In this concept module, we'll be using image analysis and NDVI to assess vegetation greenness. What are we monitoring on this global map? Let's take a look. You can see there's some dark green colors which have an NDVI value of greater than 0.5, and we have some red values there with a very low, near zero NDVI. Take a look at the tropical regions. You can see there's some bright green, and in the Tropic of Cancer here in northern Africa you can see some yellow. So we are taking a look at global vegetation greenness. Vegetative greenness can be determined using remote sensing. Red and green are regions with low NDVI, below 0.1, and typically represent barren sand, rock, or snow, while yellow and light green are regions with moderate NDVI, between 0.2 and 0.3, and typically represent shrub and grassland. Dark green are regions with high NDVI, greater than 0.6, and represent tropical or temperate rainforests. How can we determine the vegetative greenness of plants using remote sensing? Let's take a look. We can determine the amount of reflectivity from vegetation by determining how much of the sun's energy is absorbed, reflected, or re-emitted by vegetation. This all depends on the amount of chlorophyll in the plant. Satellites collect the reflected or emitted energy from the vegetation. In the top image there, you can see the green is reflected in healthy vegetation, and some of the sun's energy is also near infrared, and this can also be reflected in healthy vegetation. Let's take a closer look at chlorophyll. In green vegetation, chlorophyll absorbs most of the visible red and blue to make food for the plant, while much of the near infrared is reflected. However, in stressed vegetation, there the image in the bottom right, plants do not make food, or very much food, and as a result they reflect more red and blue and less near infrared. So I've been using this term NDVI. What is it? Well, perhaps you know, but in case you don't, it refers to the Normalized Difference Vegetative Index. NDVI is a remote sensing method that allows one to display greenness of vegetation. NDVI compares reflectivity of near-infrared and red wavelength bands. Let's take a look at the spectral signature of vegetation. Chlorophyll in plants absorbs visible light from about 0.4 to 0.7 microns. Green leaves strongly reflect near-infrared, between about 0.7 to 1.1 microns. A graph of the amount of reflection in each wavelength creates a spectral signature for that particular feature. We can determine the NDVI using image analysis. Image analysis uses remote sensing software, whether it's ArcGIS or ENVI, to determine the NDVI. And the NDVI is determined using the following formula. Near-infrared minus red over near-infrared plus red. In the left image there, you can see near-infrared is strongly reflected, while the visible has a low reflection. In a healthy vegetation, the NDVI is closer to 1, with 1 being a rainforest. In the right image, near-infrared has a weak reflection, and NDVI is closer to 0, representing a stressed plant. So let's compare the spectral signatures of healthy vegetation versus stressed vegetation. In healthy vegetation, you can see the higher near-infrared reflection, there between 0.7 to 1.1, and the lower visible reflection between 0.4 and 0.7. While in the stressed vegetation, you can see the near-infrared reflection is lower, compared to the green vegetation, while the visible reflection is higher. We can apply NDVI in GIS software, as I mentioned before, and by comparing the near-infrared and the red band using image analysis between certain dates, we can compare the amount of healthy and or stressed vegetation. This is a pretty cool image here. On the right there you can see the world according to near-infrared camera. So we're using remote sensing. Here are a couple of satellite options that we have. One option is Advanced Very High Resolution Radiometer. The AVHRR covers large portions of the Earth. It is fairly frequent, and it can be used to identify seasonal and annual changes. The key difference between AVHRR and Landsat 8 is that the resolution for AVHRR is about 1 kilometer, whereas Landsat 8 it's about 30 meters. Of course, there are other satellite options. So if you're interested in Landsat from quite a few years ago, you may be using other Landsat satellites such as Landsat 7. This is the band designations for Landsat 7. You can see band 1 is for blue, band 2 green, band 3 red, and band 4 near infrared. While Landsat 8 has different bands for blue, green, red, and near infrared. In Landsat 8, band 2 is blue, band 3 is green, band 4 is red, and band 5 is near infrared. For more on Landsat satellites other than 7 and 8, please go ahead and go to the website there in the bottom left. We can apply NDVI to monitor many physical characteristics of the Earth. We can assess agricultural production, desertification, fire production, land cover change, vegetation health, as well as for climate change. This image shows us the average NDVI for early January. You can see that there is very little vegetation in the northern hemisphere because it's winter time and many of the trees in the mid-latitudes have lost their leaves. While in the southern hemisphere you can see that there is more greenness. However, you can see in the southern hemisphere there are places in Australia that are red, and the reason for that is because those red regions are desert regions and have very little greenness. In this image we're looking at NDVI across portions of North America. This is again for early January, in this case 2006, and you can see in the northern parts of the United States and most of Canada, you can see snow and ice are on the ground this particular week. That's the white, and very little vegetative greenness there in states like Nebraska or in southern Ohio. Whereas if you go to the Yucatan Peninsula, you can see significant vegetative greenness because the trees there do not lose their leaves there in January. We can also use NDVI at various scales, from global to regional scale. This is an example of looking at NDVI for parts of Syria. You can see we're comparing 2007, when there was significantly more greenness in the northern parts of Syria, as compared to 2008, there was significantly less greenness. We can also look at NDVI at the local scale. In these two images, you can see red corresponds to higher crop yields, while blue and green correspond to lower crop yields. There's a series of questions now based on this short lecture, this concept module. The first question here, what is the normalized difference vegetation index? I'll give you a few seconds and go ahead and make a guess before we move on to the next question. Here's question 2. In stressed vegetation, plants are not making food and reflect more blank and less blank. I'll give you a second to read that question over again and make a answer. By the way, all of the answers to these questions will be in the Part 2 PowerPoint of this concept module. Number 3, an NDVI value of 0.7 might be blank, while a value of negative 0.2 might mean blank. The following letter corresponds to green vegetation. A, B, or C. So you really want to look at the microns or the micrometers between 0.7 and 1.1. What are the Landsat 8 bands for blue, green, red, and near infrared? In this image showing an area of crops, red represents blank, while green and blue represent blank. Give you a second there. And the last question. List 4 real-world applications of NDVI. Again, list 4 real-world applications of NDVI. Here are some additional resources that I found very helpful as I created this concept module and as I created my local exercise using Landsat data. The last one there, Landsat Globus, this is one way that you can acquire raster data. Here are the references. If you'd like to see the answers to the mini quiz, go ahead and see Part 2 of this concept module. Thanks a lot for viewing this concept module on NDVI and using image analysis.